The next problem we're going to tackle is entitled Finding the Greatest Common Factors. Given two numbers or three numbers or three terms, find out what you can factor out. Find the largest thing you can factor out. And you can always factor out the greatest common factor, the largest one. So let's find some GCFs. Suppose you were asked to find the GCF of 9 and 6. Okay, some of you may say, oh, I see it. 3 is the largest number that goes into both of them. Now, one way of doing it, if you don't see it, with small numbers, they have to be small numbers, is you can go one by one to find the factors. Does 1 go into 9? Yes, it goes in 9 times. That is, 9 is also a factor. Then you try, there's 1 and 9. Then you try 2. Does 2 go into 9? No, it does not. So 2 is not a factor. Is 3 a factor? Yes, it is. How many times does 3 go into 9? 3 times. I already wrote 3. Once you've already written down a number, you stop. Those are the factors of 9. Well, that's not exactly true. -1 and -3 and -9 also go into 9 evenly. 1, 3, and 9 are the positive factors of 9. Now we go to 6. What are the numbers that go into 6? Well, 1 goes into 6 times. But why do I have 6 down? Because 6 also goes into 6 then. Okay, we tried 1. Does 2 go into 6? Yes, it does. It goes in 3 times. Okay, we tried 1, we tried 2, now I'm going to say 3. Does 3 go into 6? Oh, I already wrote down 3. Once you already wrote down one of the numbers, you stop. Then you say, okay, I have all the factors of the 2 numbers. They both have 1 in them, maybe the answer is 1. But 1 is called a common factor. They're in both lists. 3 is also a common factor. But I can say more about 3. It's the largest, it's the greatest common factor. As a result, the problem is done. Okay, so let's do another one. Suppose you were asked to find the GCF of, say, 15 and 20. What is the largest number that goes into 15 and 20? Some of you, boom, 5. You just see it. 5 goes into 15, 5 goes into 20, and nothing larger goes into 15 and 20. If you see it, put down 5. If you don't see it, write down the prime view. Write down the factors of 15. 1 goes into 15. 1 goes into every number. How many times? 15 times. In fact, the number itself always goes into itself. 9 goes into 9, 12 goes into 12. So we have 1 and 15. Does 2 go into 15? No. Does 3 go into 15? Yes. How many times? 5 times. 3. Does the next number 4? Does 4 go into 15? No. Next number is 5. Does 5 go into 15? Oops. I said a number that I already wrote down. You stop. These are the factors of 15. Now we go to 20. 1 goes into 20 times. That is 1 and 20 are factors of 20. 2 goes into 20 10 times. Does 3 go into 20? No. Does 4 go into 20? Yes. 5 times. I said 1, I checked 1, 2, 3, 4. The next number I'm going to check is 5. Oops, I already have 5 down. I can stop. I didn't mean for the 5s to end up being underlined. Well, again, we have some common factors, like 1. We have 5 are common factors. In fact, 5 is the largest or the greatest common factor. That's why that's the answer. Now that's one way of finding the GCF of two numbers. The only problem is if the numbers are really, really large, you might have to go through an awful lot of factors. For example, if I now ask you to find the GCF of, say, 280 and 1100. Let's find their factors of 280. Well, 1 times 280 is 280. And 2 goes into 280 140 times. 3 does not, but 4 does. 4 goes into 280 70 times. 5 goes in there. It goes in there 56 times. You're going to have to know your multiplication. You have to know how many, or do long division. How many times does 5 go into 280? I just hate this problem. Okay, does 6 go into 280? No, it does not. But 7 goes into it 40 times. 7 times 4 is 28. With 0, gives me 280. 8 goes into 240. 8 goes in there 35 times. 9 does not go into 240. 10 does. 10 goes in 28 times. I actually ran out of room. Does 11 go into 280? No, it does not. 12 does not. Does 13 go into 280? Probably not, but let's check. That's 26. 13 doesn't go into 20, no. Does 14 go in? The answer is, you better believe it, 14 goes in 20 times. 15 does not go in. Does 16 go in? No, it does not. I don't think 17 does. I don't think 17 goes into 280. 17 times 6 is 42. Yeah, it does not. Does 18 go in? No. Does 19 go in? I doubt it. Does 19 go into 280? One time? No. And 20 I already have. So the two numbers that I didn't have room for, there's only 2 of them. So I'll kind of stick them in. I'm pretty good at finding factors, and this took me a while. If you're not good and you don't have a calculator to use, you roll your pain. There were 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 different factors. You know what? 1100 is even larger than 280. So you want to come up with another way of doing this when there's large numbers. Now, the first 2 cases I gave, the first 2 examples I gave, these examples here, they work very well using the technique that I just did. But you can use this new technique, the one that you definitely should use for large numbers. So if you don't like learning more than one technique, don't do the first technique. Only do this new one. This new one should definitely be used for large numbers like 280 and 1100. You can also use this new technique that I'm about to show you for small numbers. But you can use the first technique that I showed for small numbers. So rather than showing a new technique with the large numbers like 280 and 1100, let's show it for the smaller numbers. 15 and 20. What you want to do is just find the prime factorization. 15 is 5 times 3. Both of these are prime. That wasn't bad. 5 times 3. 20 is 4 times 5. 5 is prime, but 4 can be broken down to 2 times 2, and the 2's are prime. So 2 times 2, or 2 squared, times 5. That's the prime factorization of 20. Now, to find the GCF, of 15 and 20, you look here and here. And you write down the bases that were in both of those boxes. The bases here are 5 and 3. The bases here are 2 and 5. The common base was 5. Now you look for the smallest power of 5. You look for the smallest power of 5. Here is 5 to the 1, at least the 1's understood, and likewise 1 is here. Between 1 and 1, between these two numbers, which is smallest? 1. 1 is smallest. So the answer is 5 to the 1 or 5, which we got a few minutes back. But I think this took a little bit longer. But for large numbers, you definitely want to do it this way. What's the cutoff? When does it become large and small? It's a matter of how good you are with finding factors. Okay, 280. That is, I don't know the answer to that. 280, well, it's 28 times 10. 28 is not prime. It's a 4 times 7, 14 times 2. The tree is not unique. What I write down here will be. If two of you do it, you have to get the same answer. Okay, 7 is prime, 4 is not. 4 is 2 times 2. The 2's are prime. 10 is 5 times 2, both of which are prime. So the prime factorization of 280 is 2 times 2 times 2, or 2 cubed, times 7 times 5, times 7 times 5. Okay? And now we do the same thing for 1100. 1100, well, that's 11 times 100. And 100 and 11 is prime. 100 is 2 times 50. 2 is prime. 50 is 2 times 25. 2 is prime. 25 is 5 times 5. The 5 is a prime. So the prime factorization of 1100 is 11 times 2 times 2, which is 2 squared, times 5 times 5, which is 5 squared. Okay, now we're ready to write down the answer for the GCF. We look at the different prime bases, 2, 7, and 5. 11, 2, and 5. And we ask ourselves, which bases were in both of these prime factorizations? Which bases are here and here? And the answer, I hope, is obvious. This has 2 and 5, and this has 2 and 5. The like bases were 2 and 5. Now we need to go and find the smallest power of 5. Well, let's go with 2 first, because I wrote down 2 first. The powers of 2 are 3 and 2. The smaller one is 2. When it comes to 5, there's an understood 1 here, and there's a 2 there. Between 1 and 2, 1 is smaller. So here's the answer. 4, 2 squared is 4, times 5 to the 1. It's 4 times 5, or 20. The GCF of 280 and 1100, 20, equals 20. It's a lot easier than writing down and that's not much writing it down, deciding on which are the factors of 280. Okay, so that's done. Now, if you notice, the problems we've done so far only has numbers. Find the GCF for this number and that number. Well, you might find letters. Now, let's just do one more with numbers. Suppose I gave you the prime factorization. I told you The first number is 2 cubed times 7 squared times 13 to the 5th times 11 to the 9th. These all should be prime numbers, and they are. Find the GCF of that number and 2 to the 5th, 17 to the 3rd, times 13 to the 9th, times 29 to the 11th. If it's given to you that way, you just have to find the like bases. Like there's a 2 here for a base and a 2 here. There's no 7 in the second number. There is a 13 in the second number. The 13 is common. There's 11 in the first, but there's not an 11 in the second. So the GCF is going to be 2 to some power times 13 to some power. The like basis. The power of 2, or the powers of 2, were 3 and 5. We use the smaller one. 13 was common in both of these numbers. 13 to the 5th, 13 to the 9th. Between 5 and 9, we pick the smaller number. And I know what 2 cubed is. For homework, figure out what 13 times 13 5 times is, and multiply the two numbers, and you'll have the answer. Okay, what I'm trying to show is, if it's in prime factorization, it's easy to do. Now, there's a reason I gave you this problem. And that's because when it comes to letters, like if I ask you, how do you write the letter X as a product of primes? I mean, you have no way of knowing, well, come on, X is a squared times b to the 4th. You don't know that. X is X. So, when you have letters, you think of the letters as being prime. So, if you have X to the 5th, Y to the 7th, Z to the 9th, W to the 13th, comma, R to the 5th, S to the 9th, X to the 11th, and Z cubed, and T to the 4th. And I didn't mean to put commas in all those places, sorry. So we're finding the GCF of two terms. This term and that term. That's the T at the end. Now, when it's letters, we think of the bases as being prime. So we find the common bases. This has an X, so does this one. This one has a Y, but the second term does not. This has a Z, and so does the second term. This has a W, but the second term does not. The only thing that they have in common for bases are X and Z's. So the answer will be X to some power times Z to a power. When it comes to X, the powers are 5 and 11. We write down the smaller one. When it comes to Z, the powers are 9 and 3. We write down the smaller one. Problem is done. The letters are much, much easier than the numbers. The numbers, first you have to write the numbers like this. Like we did with 15. We said 15 is 5 to the 1 times 3 to the 1. And we said 20 was 2 squared, which is 4, times 5 to the 1. So, in finding the GCF of 15 and 20, we're really finding the GCF of 5 to the 1 times 3 to the 1 and 2 squared times 5 to the 1. And the common bases were 5, and between 1 and 1, 1 is the smaller one. 5 to the 1 is 5. Okay, but the problem is we had to write it down in prime factorization. We actually had to do that calculation. With the letters, it's already done. So, sometimes in algebra, you really rather have letters because they're easier to deal with. I'd rather do addition than multiplication. If somebody asks me what x cubed times x to the 9th is, I'd rather add those two numbers. Somebody says 3 cubed times 2 to the 9th, how much is that? This is a disaster. You may know that 3 times 3 times 3 is 27. But what's 2 to the 9th? What's 2 times 2? 9 times. 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, this is 16, and this is 16. 16 times 16 times the last 2. 16 times 16, I'm pretty sure, is 256. Times 2 is 512. So now I have to multiply 27 by 512. Actually, you do. That's too hard for me. It was much easier to do this problem. So sometimes the letters are better. If you don't know what x is, you can't raise it to the 12th power. I guess my example wasn't very good because when it came to the letters, sorry about that, when it came to the letters, the bases were the same. But when it came to the numbers, I did use different bases. I guess I blew that. If I ask you, what's 7 cubed times 7 to the 9th? Well, we know it's 7 to the 12th, but now you have to multiply 7 by itself 12 times. I wouldn't want to do that. Okay, so now, what if I ask you this problem? Find the GCF of 7a to the 5th, b to the 7, c to the 8, 14, b to the 14, c, d to the 103. You need to do the number separately. GCF are 7 and 14. 7 is just 7, and 14 is 7 times 2. They only have one 7 in common. So let me put the answer here. So we know 7 is going to be part of the answer. And now comes the easy part, the letters. This has an A, this number does not. This has a B, this number does. So they have B in common. So I know B will be part of the answer. This has C, so does this. C will be part of the answer. Then I look at the powers of B and the powers of C. The power of B, these are 7 and 14. 7 is the smaller one. The powers of C are 8 and the understood 1. The understood 1 is the smaller one. So you don't have to write the 1, C to the 1. Because C to the 1 is just C. So I erase the power. And there's the answer, 7b to the 7c. Somebody else can do this problem correctly and say this. Multiplication does commute. But you really, really should have the number first. That is, you shouldn't say b to the 7c, 7. That, I don't know if I want to say it's wrong, but it's grammatically incorrect. It's bad grammar. Yes, math has grammar. You should write 2x, not x2. How about this problem? Find the GCF of 36 times a plus b squared times c times d and 27 times a cubed times b cubed times c to the 5th times e to the 11th. In the first term, 36 times a plus b squared cd. The factors, like always, are the things that are being multiplied. 36 times a plus b squared times c times d. there is no factor of A. There is no factor of B. There are two factors of A plus B. Think of stuff in the bracket as one letter. Think of it as R squared. Okay? A and B are not factors. Things that are being multiplied are factors. A plus B is not a factor. A and B are not factors. A plus B is. Okay, so now, unfortunately, we have numbers. 36, and there's a lot of numbers that go into 36. 1 and 36, 2 and 18, 3 and 12, 4 goes in 9 times, and 6 goes into 6 times. That second 6, well, I don't have to write down because I already wrote down 1. There are 1, 2, 3, 4, 5, 6, 7, 8, 9 numbers that go into 36. And 27, well, I shouldn't say equals, excuse me. When it comes to 27, 1 goes into 27, and so does 27. 2 does not go into 27, 3 does, 9 times. 4 does not go in, 5 does not go in, 6 does not go in, 7 does not go in, 8 does not go in, 9 does go in, but I already have it. So I stop. I'm going to write these numbers a little bit closer. These are the 4 numbers that go into 27. On both lists, the largest number is 9. I wouldn't do it that way. 36 is a large number. 27 is a little bit large. 36 is 9 times 4. 9 is 3 times 3, and 3 is a prime. And 4 is 2 times 2, and the 2's are primes. So 36 is 3 squared times 2 squared. And 27, well, that's 3 times 9. 3 is prime. 9 breaks down to 3 times 3, and the 3's are prime. So it's 3 cubed. Between here and here, the common base is 3. So when it comes to GCF, it's going to be 3 to a power. So we want to find the smallest power. The powers of 3 are 2 and 3. 2 is the smallest. So it's going to be 3 squared, which is 9. Okay. Then we continue. A plus B is the next factor thing in the first term, but it's not here. C is a factor in the first term, and there it is in the second. Understood 1, 5. Smallest power is the understood 1. You don't have to write down the 1. B is in the first term, but it's not in the second term. So we're done. There's no point in even talking about E. I went through every factor in the first term. I never said E. The reason I didn't say E was E wasn't a factor in the first term. So the final answer is 9C. If you were adding these two terms, if there was no GCF, there's not a GCF, but rather you were just doing ordinary addition. You were adding these two. Oh, you would factor out 9C. Okay, you would factor out 9C. And next section, we'll talk about what would end up in those parentheses once you factored out the 9C. Okay, now, as I mentioned at the very beginning, you can find the GCF of 3 numbers. There are 3 terms. What's the largest number that goes into 9, 12, and 15? you might realize it's 3 right off the bat. Or you can say 9 is 3 times 3. That is 9 is 3 squared. You should know that 12 is 3 times 4. But 4 is 2 squared. 12 is 3 times 4. 3 is prime. But 4 is not. 4 is 2 times 2. So it's 3 times 2 squared. Excuse me. And 15 is 5 times 3. 15 is 5 times 3, and both of those are prime. So then I look for the common base. There's only one base here, 3, and it's in all 3 of them. Nothing else can be common. You can't tell me 5 is common in all 3. The first term, the first number only has one base. So 3, and the powers are 2, the understood 1, and the understood 1. Between 2, 1, and 1, what's the smallest number? 1. So it's 3 to the 1, which is just 3. And we're done. But what if we have a more complicated one? What if we have 3 terms and it has numbers and letters? It's harder. Suppose you wanted to find the GCF of 14 a cubed b squared times c plus d to the 5th, 21 a to the 9th, c to the 5th, and I don't know, 7 b to the 4th, c to the 5th. Suppose you wanted that. Well, first, the hard part, the numbers. The only number that goes, 7 is prime. The only number that goes into 7 is 1 and 7. Well, 7 goes into 14 and 7 goes into 21. The answer is 7. And you want to work it out. 14 is 7 times 2. 21 is 7 times 3. 7 is 7. They all just have one factor of 7 in common. Okay, now for the rest. The first term has an A. The second term has an A. The third term does not. So no A. The first term has a B. The second one does not. No B. The third one has C plus D. The second one does not. For the record, the third one did not. So and there's nothing else in the first term. So only 7 is common in all 3 of them. Okay, on that note, this finishes the section entitled Greatest Common Factor. Good luck with